Solids have some definitions to give you, right? And then, but basically, the first concept in the formation of solids is Hooke's law. Remember Hooke's law? Force is proportional to extension, right? But Hooke's law is only obeyed where? Until the elastic limit is exceeded. Well, the proportional limit is exceeded, right? Right? And beyond Hooke's law is where things start to get what? What would happen if you go beyond Hooke's law? Right? And instead of things being elastic, it now starts to become flat. Okay? Plastic, yeah. Yeah. Instead of if it's now elastic, it's plastic. Alright? Alright, kind of deformation of solid. Forces applied to material. That right, right? That will have the soft copy for this. Forces applied to a material. I know a bit of writing, right? Forces applied to a material may cause it to become deformed. May cause it to become deformed. Full stop. The material is said to be stressed. The material is said to be stressed. The material is said to be stressed and underline with stress. And as a result is said to become strained. And as a result is said to become strained. Right? So as I go along, I'm just writing down important words, right? May cause it to be deformed. Right? That's the heading, right? Deformation of solid. Right, so we're going to focus on stress and strain. Before we do that, just write these words down and give it a meaning. Tensile stress and compressive stress. Right, tensile stress results in an increase in length of the material. Tensile stress results in an increase in length of the material. Tensile stress results in an increase in length of the material. Increase in length. And length of the material. Compressive stress results in a decrease in length of the material. Results in a decrease in length of the material. Right? Decrease in length. Okay? Again, we come back here, that's now, right? To these two words. Before we come to that, let's take a look at Hooke's law. Right? Hooke's law states that. Hooke's law states that. Online, you're hearing, right? Hooke's law states that the extension of a spring. Hooke's law states that the extension of a spring is directly proportional to the applied force. is directly proportional to the applied force. Provided that the proportional limit of the spring is not exceeded. Provided that the proportional limit of the spring is not exceeded. Provided that the proportional limit is not exceeded. Right, so of course you might remember this, F is proportional to F. F is equal to Kx. And you know that K is your spring constant, right? What's the SI unit to K? Jacob? Newton divided by? Hello? Right? You might remember this graph, of course. You might remember this graph. If you have the graph of force with its extension, how does it look? Right? Right, nice straight line up until the proportional limit. Let's call that A. And once it go beyond that, right, let me just draw it like this for now. I'll expand in that middle piece just now. It looks like that, right? Once you go beyond that proportional limit, right? Once you go beyond that proportional limit, what has happened is that it's no longer starts at O. It starts at some other point because it's permanently stretched, right? Because it becomes permanently stretched. Right, sorry. Right? Small thing on your choice already? Yeah. Right, your choice already. Take a small note. O to A is a straight line. O to A is a straight line where force is proportional to extension. You were in this last week. I'm not. O to A is a straight line. O to A is a straight line where force is proportional to extension. where force is proportional to extension, right? Here to here is a straight line, right? Where force proportional to extension and the spring obeys Hooke's law, right? And the spring obeys Hooke's law. And the spring obeys Hooke's law. After extension, the spring obeys Hooke's law. Quick question. What does the gradient of this graph represent? What does the gradient here represent? What's the gradient of this part of the graph represent? Huh? No, remember it's a force extension graph. No, just the gradient. The gradient is spring constant. Gradient is always force divided by extension. Well, it's K. F divided by X is K. What? Turn around, yeah. Right? A is the proportional limit. Capital A is the proportional limit. Capital A is the proportional limit. Beyond which the spring no longer obeys Hooke's law. Beyond which the spring no longer obeys Hooke's law. Yeah. Yeah, form 6 not working out, so we start. We back on form 5. Right? We're back on form 5. Right, note that the elastic limits. Still right, then. I've got plenty to write. Yeah, you will have this for people as well. Yeah, they're right. Note that. No, right. Note that the elastic limit. Note that the elastic limit is the maximum load. Note that the elastic limit is the maximum load which can be exerted on the spring. The maximum load which can be exerted on the spring, and it still regains its original, size and shape. There's a chance I might be here next Friday, right? I must do it tomorrow evening. Right? But I have a class going on still. On some questions, right? Somebody has to be doing it. Yeah. Questions that we have to do. It's more than one, some call it. But I'll start home tomorrow and tell it. All right. So the elastic limit is the maximum load which can be exerted on the spring, and it still regains its original size and shape. Right? Its original size and shape. Note that the elastic limit, there is second note that Note that the elastic limit is sometimes coincides at the same time. Coincide with the proportional limit. All right. Right, you'll get a little break from writing plenty things now. So now we want to go to 3 new quantities. Stress, strain, Young's modulus. Right? We want to take a look at each one of them here. But let's get this symbol right here. One is capital E. One is the funny looking E. Oh, which one? No, this one's a capital E. Oh, which one? Yeah, but the capital funny. If I capitalize that, is okay. Right? But this is of lowercase epsilon. I remember this symbol here. Right. So we're looking at these 3 quantities here: stress, strain, and Young's modulus. You all ready? Sylvester, already? What's your name? Right. So we're looking at these 3 new quantities, right? The stress experienced by the spring is given by the force acting per unit area. Are you familiar? Force on area is what? Pressure. Right? Strain is a ratio. Right? Strain is a ratio of the original length to the extension. Is that color? And last one, Young's modulus. Marquis, all the time the same. I'm gonna do the rule. That's not the right. And last one, Young's modulus is the ratio of stress over what? Strain. Right? And we could kind of rearrange it, plug in these two, and it will look like this, right? By the way, before I write anything, what's the SI unit for strain? What is? Not wrong. I don't have any. It's 2 lengths. 2 lengths, right? What about here? What's the SI unit for Young's modulus? But stress have 1 pascals. So the SI unit is pascals, right? Right. Please note that we can also write Young's modulus like this: stress divided by strain. So that'll be FL over AX. That's Young's modulus, right? Young's modulus could also be written like this: FL over AX. Right, and write your own note on what in definition page 1. Huh? Yeah. No, that's that. Yes, sir. We are finished one module 3 here is the last one. Right, and then we start module. Yeah, so I don't have enough number 4 now. That's one and we have to come.
We don't have to start on the tree where else.
Yeah, but it is the end of module 3. Right. Put us in words, please. Trestles, force acting per unit area. Strain is the ratio of extension to length, original length. Young's modulus, ratio of stress to strain. Right? Put these three in your own words, please. Anthony Hussein, he the class. You're on class, right? Or the X on the end, right there, you, that's weird. Come on, hurry up, write that down. Sorry? You're fine? Right, I have a little question here for all the maths people. I'm going to plot the same graph, F versus X. Right? Can you tell me how to get Young's modulus from this graph? You give it an answer right now. Everybody else. Right? What I want you to do, right? Use this relationship here. Right? We plot a force versus extension graph. And I want you to tell me how we could get Young's modulus from that graph. From the graph. Right? Provided, of course, you have length and area, of course. Right? Provided you have length of the string and the cross-sectional area. Multiply closely. I like how you think it. I like how you think it. Do my favor, put this formula in the form y is equal to mx plus c. Right? Put it in the form y is mx plus c and see how you can get Young's modulus. Oh yeah. Ready? Right, so if we rearrange the formula, right, remember, I'm rearranging this formula here, right? If we rearrange this formula here, we'll get FL is equal to EAX. Bring the L on this side. Sorry. Bring the L on this side and we'll get FEL dot X. So if you plot this on your y-axis, this has the gradient, and this has the x-axis, then your gradient is this. Your gradient is equal to EA on L. So my original question to you was how to get Young's modulus from the graph. All we have to do is say Young's modulus is the gradient by the length of the wire all over the cross-sectional area. That's okay? This is a real popular question, right? So sometimes they ask you to give you a stress versus strain graph. Sometimes they give you a force extension graph. You have to be able to take this, put it in the form, y is mx plus c, and tell them how to get Young's modulus. Right? We're going to do one of this now. Wait, you can ask me to. That's okay. That's perfect. Yeah, tell me. Yeah. I'll flip it over. I'll probably give you a different version. Because sometimes they could give you a different quantity. So you could plot an X versus F graph and you have to flip it over. Right? Yeah, it has different versions. It has different versions of the graph. So basically, if I give you a graph like this, gradient, length, area, we can find Young's modulus, right? Let's see if I can give you one with some values. That's the problem. I don't want to plot this now, or it will take 2 classes to plot it.
Right, now I can write it to a project, see us sometime.